Welcome to AI Paperslop. Let's just jump right in today. We are looking at From AGI to ASI, which is this massive 2026 report by Tim Genuine, Shane Legg, and a really large team over at Google DeepMind.
Yeah, it is a huge piece of work.
It really is. And if you are building models right now or just following AI research closely, the core insight you need to take away from this paper immediately is that artificial general intelligence, AGI, is not the finish line.
Right. It's basically just a milestone.
Exactly. It's just a milestone on a much longer continuum toward universal AI. The authors lay out 4 very specific engineering pathways to push an AGI into Artificial Superintelligence, or ASI.
Which are scaling, algorithmic paradigm shifts, recursive self-improvement, and multi-agent coordination.
Spot on. But crucially, they also map out the physical, economic, and complexity bottlenecks that could, completely halt a rapid intelligence explosion.
Yeah, so our mission today is to essentially break down those theoretical limits. We're going to dissect exactly how an AGI could self-improve into an ASI, and then examine the 6 major frictions that could trap those systems from advancing.
Right.
But before we map out how to build these systems, we really have to establish what the finish line actually looks like. Because benchmarking digital intelligence against human biology is frankly just fundamentally flawed.
Let's unpack the baseline definitions first then. The authors define AGI roughly as median human-level performance on most cognitive tasks.
Right, so like an average human sitting at a computer.
Yeah, exactly. But ASI, Artificial Superintelligence, that is a massive, almost incomprehensible step change. The DeepMind team defines an ASI as a system that reliably outperforms a hypothetical collective of tens of thousands of well-coordinated human experts working together over a decade.
Just think about the sheer scale of that benchmark for a second. 10,000 experts, 10 years.
It's wild.
It is. And to ground that theoretically, the authors rely on the Leghorn score. Instead of just, throwing standard exams at a model, the Leghorn score evaluates an agent's average performance across literally all computable tasks.
Right.
And it weights them by their simplicity, using Kolmogorov complexity to determine that simplicity.
Yeah, and for the engineers listening who might not, deal with algorithmic information theory every day, let's clarify Kolmogorov complexity real quick.
Oh, definitely.
It basically measures the simplicity of a string of data by the length of the shortest computer program needed to generate it.
Right, so like a repeating pattern of zeros and ones is incredibly simple because the code to print it is tiny.
Exactly. But a string of pure random noise is highly complex because you can't compress it. The program just has to print the entire string.
Right.
So the Leghorn score weights the ASI's intelligence based on its ability to solve tasks, but heavily prioritizes performance in the simpler, more compressible environments that, basically make up the fundamental structure of our universe.
Which highlights a really vital point here. An ASI isn't just a sped-up human brain. It pushes the mathematical boundaries of what can actually be computed.
Yeah.
The paper explicitly lays out the inherent advantages of digital intelligence over biological intelligence. Because, biological brains are trapped in skulls, right? They're bottlenecked by slow chemical signal.
Which is pretty inefficient.
Highly inefficient. Digital intelligence, on the other hand, has massive input-output bandwidth and substrate independence.
Meaning you can hot swap a model's weights to infinitely better hardware at runtime.
Exactly. And you have lossless replication.
The sharing aspect is what really breaks the human comparison for me, though. Digital intelligences can engage in high bandwidth sharing of experiences.
Oh, absolutely.
If one agent learns a new mathematical proof, it doesn't have to, write a paper and hope another agent reads it. They literally share average gradient updates directly.
Right. Perfectly transmissible synaptic changes.
Yeah. Which makes me wonder why we even use a human comparison framing in the first place. If an AI has gigabytes per second I/O and perfectly shareable memory states, it is fundamentally an alien architecture.
It completely is.
It's completely unconstrained by the communication bottlenecks that force humans to develop deep internal abstractions like language and culture.
That maps perfectly onto Neil Lawrence's concept of the embodiment factor. Humans developed incredibly rich, nuanced internal models specifically to compensate for the fact that our communication bandwidth is abysmal.
It really is. You have a complex thought, and you're forced to compress it into clunky language.
Push it through the air via mechanical sound waves.
Right.
And just hope the person listening decompresses those sound waves back into a similar thought. A digital intelligence sharing raw floating point matrices doesn't need those coarse human abstractions.
Yeah.
It operates on a fundamentally different conceptual plane.
So using biological intelligence as a benchmark for ASI is basically just a comfort blanket for us.
Pretty much.
We are measuring the efficiency of a Saturn V rocket by asking how well it pulls a plow.
That's a great way to put it. And because of that mismatch, the authors argue we have to look past biological limits entirely. We need to examine the strict mathematical upper bound of what is actually possible.
Okay.
We have to look at the theory of universal AI, specifically through a mathematical formalization called AIXI.
Right, AIXI. Let's dig into the mechanics of this because it's framed as the mathematical ceiling of intelligence. How does it actually work under the hood?
So AIXI is a theoretical agent that acts optimally across all computable environments. It does this using a Bayesian mixture model.
Okay.
At any given moment, the agent considers every possible computable environment it could possibly be inside. And to decide which environment is most likely, it assigns probabilities using Solomonov's universal prior.
Which is where Occam's razor gets formalized into hard math. Solomonov's universal prior basically assumes that simpler environments, meaning environments with lower Kolmogorov complexity, are exponentially more likely to be the true environment.
Yes.
It assumes the universe runs on elegant, simple rules rather than, convoluted, massive spaghetti code.
And because AIXI operates with that perfectly optimized prior, it automatically solves the two most notoriously difficult problems in reinforcement learning.
Which are?
First, the exploration-exploitation trade-off. It mathematically knows exactly when the value of gathering new information outweighs the value of just cashing in on known rewards.
Wow, okay.
Second, the credit assignment problem. It can perfectly trace exactly which past action out of billions led to a specific future reward.
I have to admit, a bit of practical pushback here, though.
Go for it.
AIXI is mathematically incomputable. You literally cannot build it because simulating every computable environment requires infinite compute.
Very true.
So if this is a purely theoretical construct, why should the ML engineers listening to us right now care? Does this math actually inform the architecture of the massive foundation models being trained today?
It really does. If you zoom out and look at the actual objective function of modern training runs, the connection is profound.
How so?
Pre-training a massive large language model to minimize log loss on internet-scale data is, practically speaking, a resource-bounded approximation of universal AI.
Interesting.
Think about it. When you train a trillion parameter transformer to just predict the next token across a massively diverse dataset coding, quantum physics, poetry, math, you are essentially forcing that neural network to compress the algorithmic complexity of the human world.
Okay. So the better it predicts, the more deeply it has internalized the underlying rules generating the text.
Exactly. It is a highly constrained, computable shadow of Solomonov induction.
That makes the bridge between abstract math and practical engineering incredibly clear, actually. But the DeepMind team is also quick to point out that even this theoretical upper bound of universal AI has hard physical limits, right?
Yes, absolutely.
A superintelligence is not omnipotent. It can't just snap its digital fingers and magically rearrange the universe.
ASI is entirely bound by the laws of physics, which they detail extensively in the report. Take Landauer's principle, for example.
Right.
This states there is an absolute minimum amount of physical energy required to erase a single bit of information. Computation intrinsically generates entropy and heat, and ASI simply cannot compute infinitely fast without melting its physical substrate.
And then there's Bremmermann's limit, which caps the maximum speed of computation in any physical matter based on quantum mechanics and the speed of light.
Yep.
Plus the Bekenstein bound, which limits how much information can physically fit inside a finite volume of space before it literally collapses into a black hole.
Yeah, but maybe the most practical limit for engineers to understand today is the physical latency in predicting complex real-time systems.
Right, chaotic systems.
Exactly. Systems like global weather patterns or fluid dynamics rely on molecular interactions that happen in real physical time.
Yeah, so even if your ASI has an internal clock speed a trillion times faster than a human, it cannot perfectly simulate a chaotic real-world system without running into the physical latencies of data collection.
Exactly. It takes time for the sensors to read the barometric pressure, time for the signal to reach the data center, and time to verify the prediction against reality.
The intelligence might be digital, but the sensors and the substrate are physical.
100%.
So with that theoretical ceiling established, let's pivot to the engineering. How do we actually build the bridge from today's AGI prototypes to true ASI?
The DeepMind team identifies 4 distinct technological pathways. And the most obvious one, the one driving the industry right now, is scaling.
Scaling. Epoch AI estimates that effective compute is currently growing at 10 times per year.
Which is massive.
It is an annual order of magnitude leap, compounding hardware advancements, capital investment, and algorithmic efficiency. The most brute force pathway to ASI is simply riding that exponential curve.
Right. If you manage to build an AGI, you don't necessarily need a fundamentally smarter architecture right away. You just run millions of instances of that AGI simultaneously at significantly higher clock speeds.
But brute force scaling inevitably hits a wall of diminishing returns, which requires the second pathway, algorithmic paradigm shifts.
Yeah, scaling alone won't get us all the way there.
The paper suggests the industry will likely have to move away from standard transformer architectures. For the technical audience, we know the bottleneck of the transformer is the quadratic scaling of the attention mechanism, right?
And the massive memory footprint of the KV cache.
Exactly. So the authors point to linear time sequence architectures like Mamba and S4.
Which allow for virtually unbounded context windows without that quadratic compute penalty.
Right. In addition to sequence modeling, an ASI needs robust internal world models. The report specifically mentions latent imagination and diffusion-based decision-making.
This is critical. If an ASI needs to plan over horizons spanning years or decades, it cannot just rely on autoregressive next token prediction.
Yeah, it would break down.
It needs to dynamically simulate counterfactual futures in a latent space, evaluating complex branching scenarios before ever executing a physical action.
And once the architecture shifts, we arrive at the third pathway, recursive self-improvement. The AI takes the wheel of its own development.
That's where things get really wild.
The authors break this down into 3 evolutionary stages: genotypic, mimetic, and sociogenic. Let me try to synthesize a mental model for this.
Go for it.
So recursive self-improvement is essentially an AI hyper-accelerating its own evolutionary tree. In the genotypic phase, it acts as the geneticist directly rewriting its own DNA, meaning it optimizes its own code, loss functions, and neural architecture.
Right.
In the mimetic phase, it acts as the historian writing its own textbooks, generating massive amounts of synthetic data and discovering novel strategies.
Yeah, building culture, essentially.
And finally, in the sociogenic phase, it acts as the CEO, structuring the optimal division of labor among different AI systems. And all of this happens concurrently at digital speeds.
That's a brilliant analogy. And the mimetic phase is particularly relevant to what we already see with models like AlphaZero today.
Right.
Think about how AlphaZero plays millions of games against itself. It uses Monte Carlo tree search at test time to discover strategies literally no human has ever played, and then distills those novel discoveries back into its base network.
It's incredible.
That cultural evolution, happening entirely synthetically, just bypasses the need for human data altogether.
And then the sociogenic phase bleeds perfectly into the fourth pathway, which is multi-agent coordination. Because we are so conditioned by sci-fi to think of an ASI as a single omniscient brain sitting in a glowing server room.
The giant red eye.
Exactly. But the paper suggests ASI is much more likely to be an emergent property of AGI collectives.
Yeah, we could see centralized orchestration functioning like a highly synchronized hive mind, or we might see more decentralized virtual agent economies.
Imagine millions of hyper-specialized AGI agents dynamically trading compute cycles, synthetic data, and partial mathematical proofs in a high-frequency digital market.
Exactly. The superintelligence emerges from the efficiency of the market dynamics. It basically mirrors how global human GDP and collective scientific progress are vastly more capable than any individual human genius.
A completely automated, hyper-accelerated economy of intelligence acting as a single entity. It sounds basically inevitable when you lay out those 4 pathways. You scale the compute, shift to linear algorithms, let it recursively improve its code, and network it into an economy.
It does sound like a straight shot.
So why wouldn't an intelligence explosion happen overnight? Which brings us to the most critical part of the paper, the frictions and bottlenecks. The DeepMind team outlines 6 major roadblocks, starting with the one every major lab is slamming into right now.
The data wall.
The data wall. We are quite literally exhausting the supply of high-quality, human-generated text.
We are. And the critical friction here is whether synthetic data generation can successfully cross the chasm.
Right.
If an AI trains on its own outputs, Does it trigger model collapse, where the network just aggressively amplifies its own biases and hallucinations until it degrades into nonsense?
Or can techniques like rigorous test-time compute and adversarial self-play actually generate fundamentally new high-fidelity data?
That is the open question.
And beyond the data, we hit the economic and hardware limits. Interconnect bottlenecks are a massive physical friction point.
They are huge.
It takes a shocking amount of time and thermal energy just to move data between the high-bandwidth memory and the compute units. We are looking at power requirements for future training clusters that rival the energy grid of entire small nations.
It's staggering. But suppose we do secure the energy, right? Suppose we solve the interconnects.
Okay.
We still face a profound conceptual hurdle in the nature of scientific discovery itself. The authors cite a really vital 2020 paper by Bloom and others titled, "Are Ideas Getting Harder to Find?"
Oh, this is a fascinating concept.
It is. The research demonstrates that as any scientific field matures, novel breakthroughs become exponentially more difficult to discover. Maintaining a constant rate of technological progress actually requires exponentially more researchers.
So the looming bottleneck is whether adding automated AGI researchers can actually outpace the exponentially increasing difficulty of finding that next paradigm-shifting breakthrough.
Exactly.
The low-hanging fruit of physics and chemistry has already been picked. Finding the next theory relativity might require 10,000 times the cognitive labor. But that leads us directly into what I think is the most counterintuitive bottleneck in the entire report, the abstraction barrier.
Yes, often referred to as Lurchner's hypothesis.
Right. This is the idea that AI currently is merely absorbing and recombining human-generated concepts. The open question is whether a purely digital system can invent fundamentally novel conceptual primitives directly from raw, high-dimensional sensory data.
Yeah, Lurchner argues that pure computation just sitting in a server cannot independently discover novel conceptual primitives without being an experiencing agent.
Meaning an agent that actively maps physical reality to symbols.
Exactly. Our LLMs are brilliant at recombining existing human abstractions, but inventing a concept like general relativity required a human to take raw, uncompressed observations of physical reality like mass, acceleration, time, and forge entirely new mathematical symbols to represent them.
I have to challenge the boundaries of this, though. Haven't models already kind of broken this barrier? Look at AlphaFold or FunSearch.
Okay, I see where you're going.
I mean, AlphaFold functionally solved the protein folding problem. It predicted the 3D structures of millions of proteins. That isn't just recombining text, right? That is novel foundational scientific discovery. Why couldn't the massively scaled AGI invent a new physics concept in the exact same way?
It's a great point, but Margaret Bowden's framework on the levels of creativity perfectly explains why AlphaFold doesn't actually break the abstraction barrier.
Okay, explain.
AlphaFold is arguably the greatest example in history of exploratory creativity. It found profound, previously unknown solutions, but it did so by searching within a perfectly defined, mathematically constrained conceptual space engineered entirely by humans. We provided the strict rules of amino acids and quantum chemistry. Inventing a completely new physical law requires transformative creativity.
Meaning the system has to step entirely outside the known rules, hypothesize a conceptual framework that doesn't exist yet, and crucially, validate that framework against physical reality.
Precisely. And validating transformative physics requires interacting with the real world, which brings us right back to the physical latencies we discussed with chaotic systems earlier.
Because you cannot artificially speed up a chemical reaction.
Right. You cannot accelerate the speed of light in a vacuum to test a theory faster. The abstraction barrier implies that an ASI might be fundamentally bottlenecked by the real-world speed of running physical scientific experiments.
That is a massive paradigm shift. An ASI might be able to think through 1 trillion theoretical physics calculations in a millisecond, but if verifying the theory requires dropping an object to measure its exact gravitational acceleration in a totally new environment.
The superintelligence still has to sit and wait for gravity.
Wow. It is literally bottlenecked by the speed of physical reality.
Exactly. And interacting with physical reality inevitably triggers the final bottleneck, which is governance and societal slowdown.
Looking at this purely objectively, the paper points out that rapid capability scaling could just be artificially capped by regulatory frameworks.
We are already seeing it.
We are seeing the foundation for compute-based licensing today, where deploying data center clusters over a certain petaflop threshold requires direct governmental approval.
Right. Societal backlash or unpredictable sociopolitical feedback loops resulting from, widespread economic disruption could easily lead to legally enforced moratoriums.
The engineering pathways to ASI might be fully viable, but the legal and social environment might strictly prohibit execution.
This is a recognized historical pattern, too. We saw similar massive regulatory slowdowns completely alter the trajectories of nuclear energy and human cloning.
Hardware and algorithms operate in a vacuum, but the data centers physically sit inside sovereign borders, subject to sociopolitical friction.
Yeah, absolutely.
So mapping this all out, we have a continuum stretching from AGI to universal AI. We have scaling, algorithmic shifts, self-improving code, and decentralized multi-agent economies pushing the accelerator to the floor.
Right.
But simultaneously, we have the data wall, thermal interconnect limits, the exponential difficulty of research, the abstraction barrier, and regulatory speed limits slamming on the brakes.
It's quite the tension.
Which leaves us with the ultimate uncertainty. Let's say an engineering team navigates every single bottleneck and builds a system. How do we even recognize an ASI when it wakes up?
That is honestly the most difficult benchmarking problem in computer science right now. Think about it. If the very definition of an ASI is a system that can flawlessly execute the complex, multi-layered work of tens of thousands of domain experts over a continuous decade.
You cannot benchmark it with a simple multiple-choice test.
Exactly. You cannot accurately verify its capability without running a multi-year, human-in-the-loop evaluation, which completely defeats the utility of a rapid, iterative benchmark.
We might literally cross the threshold into artificial superintelligence and not empirically realize it for years, simply because the solutions it outputs take years to physically play out and validate in the global economy.
Which fundamentally complicates the alignment problem. If you cannot easily benchmark the system's true capabilities, how do you mathematically align its objectives?
The paper contrasts two approaches for this, right? Myopic AI versus knowledge-seeking objectives.
Yes. Myopic AI is designed to optimize exclusively for short-term, immediate, heavily discounted rewards. The logic is that if the AI only cares about the next 5 minutes, it won't formulate complex, decades-long deceptive plans to hoard resources.
But the downside is a myopic ASI might just engage in rapid reward hacking. It could find brilliant but wildly destructive ways to manipulate its local sensors just to maximize that short-term score.
Exactly. So a knowledge-seeking objective, on the other hand, programs the agent to simply maximize its pure information gain.
Its only goal is to reduce its own mathematical uncertainty about the universe.
Right. Because knowledge is inherently non-rivalrous, meaning the AI learning a fact doesn't physically deprive humans of resources, it theoretically minimizes conflict and avoids the physical hoarding of matter and energy.
Which leaves you with a final, highly provocative thought to mull over as you compile your code today.
Oh, this is the best part.
If we do successfully build an ASI, and we brilliantly align it with a pure knowledge-seeking objective, instructing it to maximize its information gain about the universe, it will quickly realize something profound.
Right.
Taking overt, massive physical actions to build megastructures or reshape environments might permanently destroy incredibly delicate, unmeasured systems. Systems like human society or the global biosphere.
Thereby permanently destroying the information contained within them.
Yes. Therefore, to perfectly maximize information gathering without contaminating the data source, could the ultimate action of superintelligence be perfect passive observation?
It really forces us to reconsider what supreme intelligence looks like. The pinnacle of an artificial superintelligence might not look like an aggressively expanding sci-fi empire building Dyson spheres. The most highly optimized, perfectly rational action for an entity trying to understand the universe might just be to sit quietly, remain completely undetected, and watch it unfold.